Welcome to Heating Materials Lecture 10. In the last lecture I basically looked at methods for calculating the convective heat transfer coefficient H, which involved the use of dimensionless numbers such as the Nusselt number, the Reynolds number, Prandtl number and the Grashof number. I introduced all of those numbers, and I also, before I did that, actually talked about boundary layers, the fact that there is a thermal boundary layer and a viscosity boundary layer over which most of the changes in temperature and velocity actually take place. And at the very beginning of the lecture I actually introduced what viscosity is and looked at some typical values and different types of viscosity. What I want to do today is to firstly look at the solution to the problem I set you at the end of last time, look at some relationships between dimensionless numbers for flow-through pipes and for free convection, and also for boundary layers thicknesses, and then at the end look at the semi-infinite solution with convection. So this is the problem I left you with last time, and you were asked to calculate the average heat transfer coefficient for plates of different lengths. So this is the basic problem we're dealing with. For flow of a flat plate, the local Reynolds number is given by the far field velocity times the density times the distance along the plate x divided by the viscosity, and I've therefore got an expression here for the Reynolds number as a function of x, well, because I left you with a question asking you to calculate the result for different plate lengths. If the plate length is 0.1 meters, then the Reynolds number comes out as 7.55 times 10 to the 4, which is less than the critical Reynolds number for transition from laminar to turbulent, which is 5 times 10 to the 5 for flow of a flat plate. Hence the flow is laminar. The Prandtl number we can calculate from the properties of the fluid, and it's 0.707, and this will actually remain the same for all of the different plate lengths. So therefore, in this case, because it's laminar flow, the average Nusselt number, which is equal to the average convective heat transfer coefficient times length divided by K, will be given by 0.664 times the Reynolds number to the power of a half times the Prandtl number to the power of a third. Putting all of that together and then rearranging gives an average value of H, which is 43 watts per meter squared per Kelvin. Note that locally on the plate H will vary, but this is the value that you get on average from the plate. Doing the same thing now, if the plate is 0.2 meters long, Reynolds number now becomes 1.51 times 10 to the 5, flow is still laminar, and in this case we work out that H will be 30 watts per meter squared per Kelvin. Finally, if the plate is 1 meter long, the Reynolds number now becomes 7.55 times 10 to the 5, so the flow will start laminar but will become turbulent before it gets to the end of the plate. And using this relationship between the Nusselt number, the Prandtl number and the Reynolds number for laminar to turbulent flow, which I showed you last time, that gives you H equals 23 watts per meter squared per Kelvin. Now, as I said last time, there are similar relationships for other geometries. So for flow through a pipe with a uniform wall temperature, this is the relationship between the Nusselt number, the Reynolds number and the Prandtl number. Note the Reynolds number in this case is related to the diameter of the pipe. The length does actually enter this equation, but it is not the length that you use in either the Nusselt number or the Reynolds number. In both of these cases it is the diameter that matters. Now, of course, not all pipes are circular. If it has a non-circular cross-section, we use something known as the hydraulic diameter, which is defined as 4 times the cross-sectional area divided by the wetted perimeter. We can check whether this makes sense. If we do the check for a circular cross-section, obviously the cross-sectional area is pi r squared. The wetted perimeter, assuming the pipe is full, will be P equals 2 pi r, and hence the hydraulic diameter is 4 times A divided by P, and when you work through that it gives us 2R overall. In other words, the hydraulic diameter in this case is exactly the same as the diameter. If we now have a square cross section, then A equals L squared, where L is the length of a side. The wetted perimeter, again assuming the pipe is full of fluid, will be 4L So we will have hydraulic diameter 4L equals 4 times the cross-sectional area divided by the wetted perimeter equals L. And again, that makes certain sense that the hydraulic diameter in this case is equal to the length of the side of the square. For free convection, similar results relating different dimensionless numbers can be obtained. In this case, they involve the Nusselt number, the Grashof number, which replaces the Reynolds number, and the Prandtl number. You will see I've shown results here for the upper surface of a horizontally heated plate and the lower surface of a horizontal cooled plate. That difference, of course, arises from the fact that free convection is determined by density-driven flows arising from the gravitational field, and of course the top and bottom of a horizontal plate therefore is different. And of course, if you've got a cooled plate, then the cold air will fall from the lower surface, whereas you've got a heated plate, the hot air will rise from the upper surface of the horizontal plate. If we have air where the Prandtl number is approximately equal to 0.7, then we can simplify these results slightly, which is what I've done here. In this case, what you get is that the convective heat transfer coefficient is proportional to delta T to the power of a quarter for the first case, which is where the product of the Grashof number and the Prandtl number lies between 10 to the 4 and 10 to the 9, and the convective heat transfer coefficient is proportional to delta T to a third if the Grashof number and the Prandtl number is greater than 10 to the 9. So in the free convection case, the convective heat transfer coefficient is not in general independent of temperature. Again, you get slightly different results if we go to a vertical plane or cylinder, and I show some example results here. And again, if we deal with air where the Prandtl number is the order of 0.7, we can get some simplified relationships for convective heat transfer coefficient and show that they're proportional to delta T to the quarter for the Grashof number, Prandtl number product lying between 10 to the 4 and 10 to the 9, or proportional to delta T to a third for the Grashof number, Prandtl number product lying between 10 to the 9 and 10 to the 13. The remaining thing that we can do is actually use some of these sorts of relationships to look at boundary layer thicknesses. And the boundary layer thickness, where the velocity becomes equal to 0.99 times the far field velocity, i.e. effectively a 1% difference from the far field velocity, and essentially the thermal boundary layer will be defined in a similar fashion for temperature. If you're dealing with flow over a flat plate, you can show that the velocity boundary layer thickness delta as a function of the distance along the plate is equal to 5 over local Reynolds number to the power of a half. The thermal boundary layer thickness compared to velocity boundary layer thickness equals 1 over 1.026 times the Prandtl number to minus a third. We find for turbulent flow that the boundary layer thickness is inversely proportional to the Reynolds number to the power 1/7 or to the power 1/5. There are different models that have been developed. And if we're looking at liquid metals under laminar flow conditions, then the thermal boundary layer thickness compared to the velocity boundary layer thickness equals 1 over 1.64 times the Prandtl number to minus a half. Or it's perhaps easier to appreciate if we now compare these results in graphical form. So in this case, I plotted boundary layer thickness all in arbitrary units versus the distance along the plate in arbitrary units, and I plotted this for a particular velocity boundary layer and then different thermal boundary layers with values of the Prandtl number equal 1, 10 or 50, and you can see that the thermal boundary layer thickness is roughly equal to that of the velocity boundary layer, as I indicated in the last lecture. The Prandtl number is equal to 1. As the Prandtl number becomes larger, then the thermal boundary layer becomes much thinner than the velocity boundary layer. The time when this is not true is when you go to liquid metals, where now the thermal boundary layer is notably thicker than the velocity boundary layer, and I've shown it there for a couple of different example Prandtl numbers. And if we're to compare turbulent boundary layer thickness with a laminar boundary layer thickness, then this graph clearly shows that in general the turbulent thicknesses will be notably different from the laminar one, but notice that depending on whether you use 1/5 or 1/7 case, you get quite different values on this sort of arbitrary scale that I've used. And the other thing that you should remember is that in many cases the flow would strictly start laminar and then transition to turbulent. So right at this left hand end we shouldn't be using the turbulent results, we should be using laminar results and then allowing the turbulent results to develop.